In this video, I'm going to do a few examples of doing antiderivatives with u substitution. So if we're looking at D here, I've got cosecant of 2x plus 1, cotangent of 2x plus 1. What I notice in this one is that cosecant and cotangent have the same argument. So I'm going to start off with trying that out as my u. So u equals 2x plus 1. And remember, once you've chosen your du, du automatically follows. It's just the derivative of this, which is 2 dx. Now, as I go to make my substitutions, this will be u, this will be u, and I'm going to substitute out the dx, but it needs to be 2 dx. So what I'm going to do is I'm going to put a 2 in there, but I changed what I have, so to balance that out, I put a 1/2 out front. Now I can make my substitutions. So this will be cosecant of u, and this will be cotangent of u, and the 2 dx is du, so that's just a straight substitution. Now, there's a function that has a derivative that is cosecant u, cotangent u, close to it. The derivative of cosecant is negative cosecant cotangent, so we need a negative in here. So we got negative cosecant of u as our antiderivative, plus c. Now, we don't want to leave it in terms of u, so we do need to substitute back. I'm going to put the negative on the 1/2 out front, and I've got cosecant of 2x plus 1 from subbing back, and don't forget the plus c, because we are looking for an antiderivative, a general antiderivative. It takes a little bit of practice on deciding what to let u be. Now, one thing that we know for certain is to make the substitution, du must also be in our integral. Now, we can always adjust for a constant, as we've seen, but we can't adjust for a variable. So in looking at e, your first thought might be to let u be 1 minus 16x squared. But then your du would involve an x, and there's no x in the numerator. So that's going to be too much. In fact, what I'm going to do is I'm going to rewrite this indefinite integral first. So 1 over square root of 1 minus. Now, I can rewrite this as the quantity 4x squared dx. Now I see an inside function there, that 4x, so I'm going to let u equal 4x, which makes du 4 dx. That means I need a 4 dx in my integral, so I'm going to put a 4 in, which means I need a 1/4 outside to balance it out. So I have 1/4 the antiderivative of 1 over square root of 1 minus u squared du. Now we have a function that has that as a derivative, and that's our arc sine. So it's 1/4 the derivative of, or excuse me, 1/4 times arc sine of u plus c. And now our last step is to substitute back. 1/4 arc sine of 4x plus c. Our last one, and you might get to the point eventually where you don't do a u substitution on one like this, but I'll show you where you might use it in beginning these kinds of antiderivatives. If it's 5 raised to the x, we could do the antiderivative with our simple rule. Because 5 to the negative x falls under the chain rule umbrella, let's do it with a u substitution. In particular, I'm going to let u equal negative x, which makes du negative dx. That means I need to put a negative on my dx here, so I'm going to put a negative out front to balance that out. So I have negative the integral of 5 to the u, and then that's just my du. And now I can use my basic rule, which is 5 to the u over ln of 5 plus c. Now, what you may notice is, well, let's finish this and then we'll take a look. Now we substitute back, and we have negative 5 to the negative x over ln of 5 plus c. What you may notice is really all that happened over our basic rule is we had to make the whole thing negative. So a lot of times as you get more proficient with antiderivatives, when you notice that all it is that you have a negative x, you can take the antiderivative using your basic rule and just remember that you need to multiply it by or divide by, however you're thinking about it, a -1, just like you would with the chain rule.